All right, let's dive right in. Today, we're unpacking a wild story about how one single, deceptively simple idea brought the entire foundation of mathematics right to the edge of a total collapse. We're talking about Russell's paradox. So imagine this. You've spent years building the most beautiful, most logical structure you can imagine. Every single piece fits perfectly. And then someone comes along and asks a question that sounds so simple, it's almost childish, and the entire thing just crumbles into dust. Well, that is exactly what happened to the grand project of grounding all of mathematics in pure, unshakable logic. You see, the foundation for this whole grand project was something called naive set theory. And its core idea, this thing called unrestricted comprehension, seems totally obvious, right? It just says that for any property you can dream up, like is a dog or is an even number, there's a set that contains all the things with that property. It's simple, it's powerful, and, as they were about to find out, it was fatally flawed. To get a feel for the problem, let's think about a classic brain teaser, the barber paradox. So you've got a village barber who shaves all the men who don't shave themselves. Simple rule. But then you ask, who shaves the barber? Well, if he shaves himself, he breaks the rule because he only shaves guys who don't shave themselves. But if he doesn't shave himself, then he fits the rule. So he must be shaved by the barber, which is him. You see? It's a perfect, inescapable, logical loop. This is where the brilliant philosopher Bertrand Russell enters the picture. He looked at that barber logic and applied it to the super powerful rules of naive set theory. He came up with a property. Is a set that does not contain itself. Now, that seems perfectly fine. Most sets don't contain themselves, right? The set of all cats is not itself a cat. So, Russell defined a new set, let's call it R, which is the set of all sets that don't contain themselves. And this leads us to the killer question. Does this set, R, contain itself? Let's walk through it. If R is a member of R, well, then it has to follow the rule for being an R, which is that it doesn't contain itself. Whoops, contradiction. Okay, so what if R is not a member of R? Well, in that case, it perfectly fits the definition of the sets that are supposed to be in R, so it must be an R. Bam, a perfect, airtight contradiction. And for naive set theory, game over. And look, this wasn't just some clever little puzzle. This was a 5-alarm fire. A foundational crisis. The whole dream of building mathematics from simple, pure logic was suddenly in ruins. Because you have to understand, a system of logic that allows even one contradiction is completely worthless. You can use it to prove that 2 plus 2 is 5 or that the moon is made of cheese, anything. So as you can imagine, mathematicians and logicians were scrambling to fix this. They had to come up with solutions, but as we're about to see, these fixes felt less like building a new, solid foundation and more like just patching the cracks in a wall that was about to fall down. So the two main fixes that emerged were ZFC and type theory. ZFC basically said, whoa, hold on, you can't just create a set out of any old property from thin air. You have to start with a bigger set that you already know exists, and then you can carve a smaller one out of it. This conveniently stops you from ever making a set of all sets. Type theory, on the other hand, created a strict hierarchy. It's like saying a folder can hold documents, but a folder can't hold itself. The very question of self-membership just becomes gibberish, or, as the logicians say, ill-typed. And this quote just nails the problem with these solutions. Yeah, they worked. They stopped the contradiction. But they felt ad hoc. Like arbitrary rules bolted on just to stop this one specific problem, not because they revealed some deeper truth. That beautiful, original dream of a single, coherent mathematical universe, it was gone. But then, decades later, some thinkers started asking a really deep question. What if the problem isn't with our rules for making sets? What if the problem is with something even more fundamental? What if our whole idea of identity itself is flawed? And this is the jumping-off point for a completely new way of thinking about this, called Trinitarian Relational Foundations, or TRF. TRF comes along and says, look, when we say 4 equals 2 plus 2, that isn't just a static fact. It's actually describing a process. It's about the generative act of computation that takes 2 plus 2 and produces the result 4. Identity isn't just a label, it's a dynamic pathway. Now, to really get this, we need this cool idea of a semantic territory. Think about the number 4. It's not just the symbol 4, right? It's also 2 plus 2, it's the square root of 16, it's 3 plus 1. It's this infinite collection of all the different ways you can arrive at the concept of 4. All of that together, that's its semantic territory. So this builds a whole new model of what identity is. It's not just a simple A equals B. TRF sees it as this 3-part structure. You've got the source, which is the abstract idea, like the pure concept of fourness. You've got the expression, which is a concrete form, like the symbols 2 plus 2. And then you have the bond, which is the path, the calculation that connects the two. For TRF, identity is this whole, dynamic, generative process. Okay, so armed with this powerful new idea of identity, TRF makes its second game-changing move. It rebuilds the entire mathematical universe on 2 completely distinct levels. See, the whole reason Russell's paradox works is because it assumes that the container of everything, the totality of all sets, is just another item that can itself be put inside a container. TRF looks at that and says, nope, that's a fundamental category mistake. So the old view was this single, flat universe where everything was just a set. TRF throws that out and replaces it with this 2-level structure. There's U, the source, which is like the unbounded, pure potential for all sets to exist. And then there's S, the expression, which is the actual domain where all the sets that are generated from U live. And this, right here, is the magic trick. The whole dangerous idea of the universe containing itself is no longer a question of membership. That's what creates the paradox. Instead, it becomes a generative relationship. The source, U, generates its expression, S. That toxic self-referential loop gets replaced by a safe, one-way arrow from a higher level to a lower one. So now, with this new architecture in place, this generative identity and this 2-level universe, the paradox doesn't just get patched up, it dissolves. It completely vanishes. It becomes a question that the system is literally incapable of even asking. Here's how it works. First, that nasty collection that Russell dreamed up, it's just not a set anymore. In TRF, it's called a totality object, and it lives up at that higher U and S level, not down with the regular sets. So the rules of membership just don't apply to it. You can't ask if it contains itself, any more than you can ask if a novel contains the library it's sitting in. The question is, you guessed it, ill-typed. This table sums it up perfectly. Naive theory allowed the set of all sets, and it crashed and burned. ZFC just banned it, calling it a proper class to get it out of the way. TRF says, sure, we can have it, but in this much more sophisticated 2-level way. So ZFC avoids the paradox with a restriction, a ban. TRF avoids it by fundamentally retyping what self-containment even means. And this is absolutely crucial to understand. TRF doesn't toss out the last 100 years of mathematics, not at all. All the standard tools that mathematicians use every day, the ZFC axioms, they are all built right into TRF's set level. All this does is provide a safer and frankly more philosophically satisfying foundation for all the math we already have. So, it all comes down to 2 big, powerful shifts in thinking. First, you redefine what identity means. It's a generative process. And second, you use that new definition to build a 2-level universe. And together, those 2 ideas just solve a crisis that's been hanging over math for a century. So why does all this matter? Well, because it's not another patch. It's a principled solution that comes from a deeper understanding of what equals even means. It also aligns the very foundations of math with cutting-edge fields. And maybe most beautifully, it seems to bring back that original grand dream, a single, coherent, all-encompassing universe for all of logic and mathematics, completely free of contradiction. And that leaves us with one last kind of mind-bending thought to chew on. TRF suggests that anytime a system truly refers to itself, it has to do so by making a leap to a different level, a source generating an expression. If that's a fundamental law of logic, what could that tell us about other incredibly complex systems that have to deal with self-reference, things like language, or even a mind that is aware of itself?